After we finished chapter 6 explanation of thermodynamics, we will discuss some examples. In part A of the examples number 1, we will discuss only examples on thermal processes. The first example, we have an isobaric process. An isobaric process means constant pressure. You have to sketch a small sketch between P and V and draw the 2 points of the process. The internal energy of a monoatomic gas. When mentioned in the example mono, you will write F equals 3, CV equals 3R over 2, CP equals 5R over 2. So knowing the kind of the gas, you know F, CV, CP, and also gamma, which is CP over CV. Decreases by 50 joule. The internal energy decreases. The word decreases means that the delta U is negative 50 joules. You put the negative because it is decreasing. It's required to calculate the work done. Okay, the delta U is NCV delta T for all the processes. We can find delta T by substituting with delta U, N, and 3R over 2 instead of CV. It will give you unknown N and R. We don't know N and R. But when you want to calculate the work is NR delta T. So I will substitute with the delta T with the unknowns 1 over NR, negative 100 over 3, 1 over NR. So it will be cancelled and you can get the amount of work. The work done is negative, and this is correct because the point 1 is decreasing in volume. This is problem number 1. Or you can solve it in another way. Delta U equals NCV delta T, work equals NR delta T. Divide both equations to get rid of N and delta T. So the ratio is R to CV, and CV is 3R over 2, so the work ratio to the internal energy ratio is 2 over 3. And we have the internal energy negative 50, so the work will be negative 100 over 3 joule. Another example, a certain amount of monoatomic gas. A monoatomic gas is maintained at constant volume and cooled by 50 degrees. So constant volume is drawn as a vertical line. This is done by removing 400 joules. So the heat energy is negative 400 and the delta T is negative 50 because cooled by 50 Kelvin. How much work is done by the gas? Now I don't want to calculate anything because work in the constant volume process is 0. Remember that the work is the area under the curve, no area under this line. So because this is a constant volume process, so immediately put the work equals 0 and no calculations is needed. Another example, a monoatomic gas is cooled by 50 Kelvin, so delta T is negative 50. Cooled means negative, decrease in temperature. And again, monoatomic, you put F, CV, and CP. At constant volume, I draw a small sketch for a constant volume, and now it's cooled, so the pressure at point 2 is less than the pressure at point 1. How many moles of the gas are in the sample? We know that the Q in the constant volume process equals NCV delta T. Now the Q is 831 joule, but it's written removed. Removed from the gas means the gas loses energy. So negative 831 equals N, this is the unknown. CV is 3R over 2 because it's a monoatomic gas, and delta T is negative 50. After substituting, you can get the number of mole. Another example, we have a monoatomic gas and cooled, also it is cooled by 90 Kelvin. So the delta T is negative 90 Kelvin at constant pressure. So now the process is constant pressure, and cooling means decrease in the volume. So this is state number one, and this is state number two is less volume. When 900 joules of energy is removed, so Q is negative 900 joules from it. How many moles of gas are in the sample? Again, we want to calculate the N. So Q equals NCP delta T. Q now is NCP delta T because it's constant pressure. In the previous problem, it was NCV delta T because it was constant volume. Again, you will substitute with all the unknowns you have, and the only unknown is the N, and you can calculate the number of moles. Another example, but this example is a constant temperature. Constant temperature means isothermal process. How much work is done by 3 moles? So N is 3 moles of gas. When they triple their volume means that if you draw a sketch to the PV diagram, this is the sketch of the isothermal process. Now the volume is tripled. What is the work? From the lecture, we know that the work equals N R T ln V2 over V1, V final over V initial. N is 3 moles, R is a constant given, T is 400 Kelvin, it's given in the problem, ln 3V1 over V1, ln 3. Substitute to get the work. And now the work is positive because now we are increasing in volume. Another example, this example is adiabatic process. Adiabatic process. The work is given 25 joules. What is the change in internal energy? We know that in the adiabatic process, Q equals 0, delta Q equals 0. When applying in the first law of thermodynamics, we will find that delta U equals negative the work. It's given the work 25 joules, so the change in internal energy is negative 25 joules. You have to write the negative sign for the change in internal energy. Another example, it is stating that a monoatomic perfect gas had a heat capacity. We want to revise the terminology of heat capacity under constant volume. What is the heat capacity? We said before that the heat capacity is M multiplied the specific heat, C, or N multiplied the molar specific heat. This is called the heat capacity. And sometimes we give it the symbol Q small. So when you write heat energy equals MC delta T, or you write it NC delta T, you can also write it Q delta T. Q stands for the heat capacity. It is required to find the number of moles, the internal energy at certain temperature, and the heat capacity of the gas under constant pressure. The gas we are dealing with is monoatomic. So if the gas is monoatomic, we know that F is 3, Cv is 3R over 2, and Cp is 5R over 2. It's given that the heat capacity under constant volume is this number. So it is NCV. It is NCV, which is the heat capacity. So NCV 49.8 equals N, and CV is 3R over 2, so you can calculate N 3.99 moles. The second required is the internal energy at certain temperature. The internal energy is N FR over 2 C, or you can write it NCV T, or the heat capacity multiplied by T. So it's given the heat capacity under constant volume, just multiply it with the given temperature, but take care to be in Kelvin, and then you can calculate the internal energy in joules. The last required, what is the heat capacity of the gas under constant pressure, which is required NCP. This is what is required, the heat capacity under constant pressure. We know that Cp equals Cv plus R. So if you multiply the equation by N, so NCP equals NCV plus NR. I want to calculate NCP, so I will substitute with NCV, which is given, plus N, I calculated it, and R is 8.314 to calculate the heat capacity of the gas under constant pressure. And of course, the unit is joule per Kelvin. These examples are very trivial examples, just you are substituting in simple equations. Another example, it is given that an ideal gas requires 800 joules to raise its temperature by 10 Kelvin. So I need 800 joules to raise the temperature by 10 Kelvin under constant volume when the process is a constant volume. I will write the givens in points at constant V. Q equals NCV delta T. So this gas will take 800 kilojoules to increase its temperature by 10 Kelvin. The same quantity of gas, same N and same gas, requires 1120 kilojoules to raise its temperature by the same amount, 10 Kelvin, when the gas is at constant pressure. So the second given is at constant pressure, we have Q dash, another value of heat energy, equals NCP delta T. Now the heat energy is 1120 and the delta T is 10 Kelvin. I want to know the type of the gas. To know the type of the gas, I have to know either its degrees of freedom or CV or CP or gamma. Gamma is the percent or the ratio between CP and CV. Okay, let's have a look on this equation and the other equation. Now, if you divide both equations, Q over Q dash or Q dash over Q, whatever you want, I divided Q dash over Q. It's NCP delta T over NCV delta T. You will cancel the delta T because it is 10 Kelvin in both cases, and N, it's the same amount of gas. So Cp over Cv equals Q dash over Q. What is Cp over Cv? This is gamma of the gas. You will find gamma, it will be 1.4. The gamma is 1.4 for a diatomic gas. So that's how we know the type of gas. Another example, this example is a constant pressure process. It's given that it's a constant pressure process. And a diatomic gas, we know it's a diatomic gas. Knowing it's a diatomic gas, so F is 5, and you can find CV and CE. Cools from 455 Kelvin to 405 Kelvin. So this temperature is greater than this temperature because it is cooling down, as we mentioned before. So delta T is the T2 minus T1, delta T. Now it's required to find the number of moles, again the same idea. So we will put the equation of the Q equals NCP delta T, NCP because it's a constant pressure process. Now you will substitute with 8314 removed because this heat is removed, so it is negative. So I substitute with Q negative 8314. N is unknown. Cp is 7R over 2 because it's mentioned that it's a diatomic gas. And delta T is 405 minus 455. The final temperature is less than the initial temperature. So this gives you negative sign here. The negative will be cancelled with the other negative, and you can get the number of moles as we did before in a similar example. Another example, we have a certain amount of gas. This gas is a monoatomic gas. So a certain amount means n is unknown. We didn't mention in the example what is the value of n. A monoatomic gas means F equals 3, Cv equals 3R over 2, and Cp is 5R over 2. We have to memorize this, and you are the one who will put this data. Is at state A and finally at state B. So this gas will go from state A to state B. And it's given this figure. State A, it's given the pressure and the volume. And state B, you have the pressure and the volume, as shown in this figure. Now we have two paths. One path is linear to B directly. I have a line joining A and B. This is path number 2. Another path is constant pressure till point C, then constant volume till point B. So I have path number 1 and path number 2. It's required to calculate the three functions, the work, the Q, and the delta U in each path. Okay, first of all, we will calculate the difference in the internal energy. To get the difference in internal energy between point A and point B, it is not required to know any path because the change in the internal energy is a state function, doesn't depend on the path, it's only depending on the first and last points. So I will calculate the change in internal energy from A to B for both passes and for all passes between A and B. We will substitute in the equation of the change in internal energy N Cv delta T. Cv is Fr over 2 and delta T is the T final minus T initial, so I will write it Tb minus Ta. Now I will multiply N and R inside this bracket, and I will leave F over 2 outside the bracket as a common factor. So F over 2, open the bracket, nRT minus nR another T or T at A. From the state equation, this is pressure multiply volume at point B, and this is pressure multiply volume at point A. So why I rechanged or I changed the equation from T to pressure and volume? Because the given in the equation, the given in the problem is pressure and volumes. So it's easier to substitute with pressure or volumes. Instead, you will have to find the temperature at this point and the temperature at this point. And you don't have N, so you cannot get the temperature. You get it in terms of N and resubstitute again. So it's easier to take this form of the equation. At point B, the pressure is 2 and the volume is 6. But take care, 2 bar and 6 liter. We don't use the bar, we don't use the liter as an SI unit. Instead, we use the Pascal for the pressure and we use the meter cube for the volume. So any given you will use from this figure, you have to put it in Pascal and meter cube. That's why pressure at B is 2 and volume at B is 6. And pressure at A is 5 and volume at A is 3. Then we will multiply by 10 to the power 5 to convert from atmosphere to Pascal. And we also multiply by 10 to the power negative 3 to convert from liter to meter cube so as to have the change in internal energy in joules. After substituting, you will find the change in internal energy negative 450 joules. And remember, the change in internal energy is a state function. So the change in internal energy on path AB is the same as the change in internal energy through the path ACB. This is the first step to calculate the change in internal energy for both paths. Let's discuss path number one. Path number one is this path, which is constant pressure, then constant volume. Now I want to calculate the work done on this path. The work depends on the path because it's a path function. It depends on the path to the other point. It's the area under the curve. Now to calculate the work, so I will have to calculate work AC plus work CB. I will calculate work AC, then add work CB. CB is a vertical line, no area under the line, so no work, and CB, a constant volume, no work. So I won't calculate this one. I will only calculate the work from A to C. To calculate the work, just calculate the area under this rectangle. The area is 5 multiplied by 3. So 5 multiplied 6 minus 3, which is the 3. And don't forget to put the 10 to the power 5, the conversion, and 10 to the power negative 3, the conversion of the volume. Now we calculated the work on path 1. I can apply the first law of thermodynamics. Q equals delta U plus the work. Substitute with the internal energy with its sign and substitute with the work with its value. You will get the amount of heat when you are using the path number 1. Now we will make the same but using the other path. Now I want to calculate the work from this path AB. I will not calculate all this area. I will just calculate the area under the path, which is the area of this trapezium. You see this trapezium? This is the area I want to calculate, only this. Now I change the path, so I will change the calculated area. To calculate the area of a trapezium, we put half this height plus this height multiplied by this width. So I will make it half pressure A plus pressure B, VB minus VA. After substituting and putting the conversions, I will get the value of the work. Notice that the work of path 2 is less than the work of path 1. Why? Because, of course, we notice that path 2 has less area under it than path number 1. And work is the area under the PV diagram. And again, to calculate the heat energy is just add the same delta U and the work, you will get the change in internal energy. Another example, it is discuss the next example. It is constant volume. Let's read it together. This example states that a rigid cylinder, when it is stated in the example, the word rigid, this means that the cylinder is of a constant volume. It doesn't change its volume during the process. So mentioning a rigid cylinder means we have a constant volume process. This cylinder is containing this volume of nitrogen. So this volume will be constant all over the thermal process I have. Nitrogen, when you put the symbol of nitrogen, you know that nitrogen is a diatomic gas. At 1.04 bar, this is the pressure, and 15 degrees is the temperature. Is heated quasi-statically until the temperature is 90 degrees. So now I will increase the temperature from 15 to 90. Let's draw a small sketch for the PV diagram. Knowing that it's a rigid cylinder, we draw it constant volume diagram. And what do we know at point 1? At point 1, we know the volume, we know the temperature, and we know the pressure. Now we increase the temperature. When increasing the temperature, you also increase the pressure. So point 2 has greater pressure than point 1. That's how you sketch this PV diagram. It's required to get the number of moles and the heat and the change in entropy and sketch in the TS diagram. Let's take it step by step. Now, how to calculate the number of moles? To calculate the number of moles, you need to substitute in the state equation either at point 1 or at point 2. I will choose point 1 because point 1 I know the pressure, the volume, the temperature. I know the three state parameters. So at 1, PV equals nRT. Now the unknown is N, the number of moles. So I can substitute with the pressure, the volume R and T and get the number of moles. And again, this pressure is given in bars. So I will multiply by 10 to the power 5. And the volume here is given in meter cube, so I will not multiply by any conversion factor. R is always given in the exams 8.314, it is the universal gas constant. Now to substitute with the temperature, T1 is 15 degrees. You cannot substitute with degrees Celsius, you have to substitute with the Kelvin. That's why you have to add 273 to have the temperature in Kelvin. That's how you substitute in the state equation. The only unknown is the number of moles. Get the number of moles. The second required is the heat supplied. I want to calculate the Q. Okay, to calculate the Q, I will put the equation of the heat energy, which is NCV delta T. Why CV? Because it's a constant volume process as we mentioned before. So now you have the N, the CV. Do you remember from where I can get the CV? From the type of the gas. We said that the type of gas is diatomic. So F is 5, CV is 5R over 2, and the CP is 7R over 2. Now I want to use CV, so I will put 5R over 2 and then delta T. Now the delta T is T2 minus T1, T2 90 and T1 15. Because it's a difference in temperature, I can use the Celsius. Because difference in temperature in Celsius is the same as difference in temperature in Kelvin. The last required is, or the before last, is the change in entropy. The change in entropy for a constant volume process is having this equation N CV ln T2 over 2 T1. N CV ln T2 over T1. Now T2 must be in Kelvin because Kelvin and Kelvin. It's not difference in temperature, so you have to use the absolute value of the temperature. Then you substitute to get the change in entropy, and the unit of entropy is joule per Kelvin as we discussed before. Another example is a constant pressure example. We have 2 moles of a triatomic gas in a container expands at constant pressure. It is stated here that it is constant pressure expansion. That's why when you are sketching your process, you will draw point 1, expanding point 2 with volume greater than point 1. If the initial volume is 5 liters and the final volume is 10 liters, this is the sketch I have, and the pressure is 3 atmosphere. It's required to find the initial and final temperature, the heat supplied, the change in internal energy, and the work done by the gas and the change in entropy. Let's start. What kind of gas? Triatomic gas. And how many moles? 2 moles. So I'll summarize my givens. N equals 2, triatomic, so you write F equals 6, CV3R, CP4R. Then I will start to find how I can find the temperature. Let's have a look. We have pressure and volume, and also the number of moles is known. So I can simply substitute in the state equation P1V1 equals nRT1. The only unknown is the temperature, so P1 V1 over NR, and substitute after conversion of the units, you can find the temperature. What you calculate is in Kelvin. I can do the same at point 2, or simply, because this is a constant pressure process, when we have a constant pressure process, the temperature is proportional to the volume, so T2 over T1 equals V2 over V1. Knowing V2 and V1 and also T1, I can get T2. V2 is double V1, so also the temperature T2 is double T1. This is another simple way to find T2. Or you will substitute in the equation of states P2 V2 equals nRT. After finding the initial and final temperature, I want to find the heat, the delta U, the work, and the delta S. The heat, this is a constant pressure process, so the heat is NCP delta T. And the delta U is always NCV delta T, no matter the kind of the thermal process. And the work in the constant pressure, either P delta V or NR delta T, or simply Q minus delta U. You can substitute in any form, but for simplicity, you already calculated this one and you calculated this one, so you can subtract these two numbers and get the work. Finally, we want to calculate the change in entropy, which is NCP ln T2 over T1, and I will find it in joule per Kelvin. You have all the givens in the example, so it is very direct to substitute with all the unknowns. Another example, it is also a constant pressure. Heat of 500 joules. Now what is given? The given is Q. It supplies to 2 Newton, 2 moles. Moles, 2 moles, this is the number of moles. Diatomic gas, diatomic F equals 5 at constant pressure. I want to find the change in temperature, the work, and I find the ratio between V2 and V1. What is given? The given is heat energy. So I will start with the equation of the heat energy. Again, the heat energy is NCP delta T for constant pressure process. Now you have the Q, you have the N, you have CP. The only unknown is delta T. Find delta T. This is the first required. The second required is to get the work done by the gas. To get the work done, we have two approaches. Either to calculate the area under the PV curve, but we don't have pressure and volume like the last example, or I simply write the work as nR delta T. nR delta T, I already calculated delta T, I substitute to get the work. Then it's given temperature at 1. At 1, the temperature is 20. What is V2 over V1? Because it's a constant pressure process, so the volume is proportional to the T. So T1 equals 20 and T2 equals the same T1 plus delta T. So 20, I will convert it into Kelvin by adding 273. Then I will add the change in temperature to get T2. Now I have T1 and T2, and for a constant pressure, the volume is proportional to the temperature, so V over V equals T over T. V2 over V1 equals T2 over T1. I can get the ratio of the volume. Another example, and it's also a constant pressure example. This example, we have 100 moles of a monoatomic gas. 100 is the N, monoatomic F equals 3. Cooled, again, cooled means that this is the direction of the process, in the direction of decreasing the volume, such that the volume is reduced by 3%. So if this is V1, this is the volume at 1, V2 is less than V1 by 3%. How I can calculate it? V2 equal V1 minus 3 over 100 of V1. 3% of V1 is 3 over 100 V1. So it's 97 over 100 V1, which is 0.97 V1. So I know that V2 is less than V1 and it is less than it by 3%. If the original temperature of the gas is 24 degrees, so this is T1. This was the temperature of the gas. It is required to find the final temperature, which is T2, the heat capacity at constant pressure. What is the heat capacity? You remember we discussed before the heat capacity, it's not molar specific heat, it's N multiply the molar specific heat lost by the gas is required, and also it's required the work done, which is W. Let's start solving. This is a constant pressure process, so the temperature is proportional to V. I want to get T2. Okay, I can relate T1 over T2 equals V1 over V2. And the only unknown is T2. I can find the temperature at point 2. T2 equals T1 V2 over V1. After substituting, you can find T. The heat capacity at constant pressure is NCP. Do you know the kind of gas? Yes, I know it, monoatomic. So the CV is 3R over 2. Just multiply N by the CV. Sorry, it's required at constant pressure, heat capacity at constant pressure. So I will multiply N by Cp to get the heat capacity under constant pressure. 100 multiply 5R over 2 will give you the heat capacity. Then it is required to find the heat energy. The heat energy is NCP delta T, so I can use the heat capacity and multiply it by delta T. From where I can get delta T, I have T1 and I have already calculated T2. Simply subtract the two temperatures to get the delta T. And of course, the delta T, the final temperature, is less than the initial temperature, so you will have a negative sign. Means that the Q negative, this is heat energy lost by the gas. Finally, I want to calculate the work done. From my sketch, I can calculate the area, but I don't know the pressure to get the area. So this is not the way to calculate it. So I have to substitute in the equation. Again, if it's constant pressure, the work is nR delta T. Now the delta T is negative, so the work is negative. What is meant by negative work? It means that this work is done on the gas. This is not done by the gas, but it's done on the gas. This example is isothermal example, 5 moles, N equal 5, 5 moles, N equal 5, of an ideal gas expands isothermally at 100 degrees. So the temperature of the process is 100 degrees. I can convert it into Kelvin, and this is constant all over the process to twice of its initial volume. So if it will start with V1, it will end with 2 V1, double V1. It's required to find the heat, the work, the change in internal energy, and the change in entropy. Let's start solving. For an isothermal process, the change in internal energy is zero. So delta U is always zero for an isothermal process. And the mechanical work and the Q are equal. The mechanical work and Q are equal. So I will just calculate one equation. Q equals work equals nRT ln V2 over V1. Ln V2 ln V2 over V1 means ln 2. Temperature, put it in Kelvin, and 5 moles, and substitute with the R. You can get the amount of heat, which is the same as the work done by the gas. The last required is the change in entropy. For an isothermal process, the change of entropy could be calculated by the equation nR ln V2 over V1 or change of Q over T. Why? Because now the temperature is constant, so delta S equals delta Q over T. Already I calculated the delta Q, just divided by T, you will find this number. Another example, the work done on an ideal gas in an isothermal process is negative 400. What is the change in the internal energy? Again, isothermal process, no change in internal energy. No need to calculate anything. Just write the change in internal energy equals 0. During an isothermal process, 5 joules of heat is removed. 5 joules of heat is removed. So this is Q. Q is negative 5. And it is isothermal process. What is the work? The work done equals the heat exchanged by the gas, because Q equals delta U plus the work. Now we don't have delta U in isothermal process, so exactly the work equals the amount of. Another example, 1/2 mole of helium. Take care, 1/2, it's not 1 1/2. It's 1/2 means N equals half. Of helium. Helium is a monoatomic gas. It expanded adiabatically from an initial pressure and temperature to final pressure. I will sketch a small sketch in the PV diagram. The initial pressure is 5 and the final is 1. So this is point 1 and this is point 2. And it's an adiabatic expansion. The temperature at 1 is 500 Kelvin. And we are we have to find the final volume V2, the final temperature T2, the work done, the change in internal energy delta U. Let's start solving. At point 1, what do you know? I know the pressure and the temperature. So easily you can find the other parameter V. So just apply the state equation PV equals nRT at point 1. You can calculate the volume at point 1. Then I want to calculate the temperature at 2. How I calculate the temperature at 2? I have temperature at 1 and I want to get temperature at 2. I have pressure at 1 and pressure at 2. I can use the relation of the adiabatic. In the adiabatic relation, PV to the power gamma equals constant, which means that P1 V1 to the power gamma equals P2 V2 to the power gamma. What is unknown is V2, because P1 and P2 are givens. V1, I just calculated V1 now. So I want to get V2. So to calculate V2, I just substitute in the adiabatic relation. Now I want to find T2. Again, in point 2, after knowing the V, I can relate either T and P in the adiabatic, either I use the adiabatic relation or simply I can use the state function PV equals nRT and calculate T. It's required to get the work. The work in the adiabatic process has two formulas. Either you say work equals negative delta U, because in the adiabatic we don't have any heat exchange, or you substitute in P2 V2 minus P1 V1 over 1 minus gamma. I will use this formula, so negative NCV T2 minus T1, and I will substitute, but it is positive, not negative. What is negative is the change in internal energy. Let's explain this. When you increase in volume, this means that the work will be positive. The work is positive when you increase in volume. But although you are increasing in volume, but the temperature decreases. Why? I was beginning with 500 K and the new temperature I calculated is 262 K. So when the temperature decreases, this means that the change in internal energy will be negative. This is very important to know when it is increasing or decreasing. Another example, we have zero point 0.1 mole of a monoatomic ideal gas following the shown processes, and this is drawn. This is not my sketch. This is the example. It's required to get some parameters like the temperature, the work, the internal energy, the heat energy, and the entropy. Let's start. N equals zero point 0.1 and it's a monoatomic gas, so F equals 3, Cv and Cp are known. To get the temperature, let's examine point 1. I have pressure, I have volume, so I can get the third parameter, temperature, by substituting in the state equation. Similarly, you can do the same at point B and point C because the pressure is known and the volume is known. So at each state, you know the pressure, the volume, and also you know the amount of gas. So you can just substitute and get the temperature. Now we want to calculate the work. To calculate the work from A, B, C, we will calculate work AB first, then add work BC, but work BC is 0 because we said when constant volume we don't have work done. So when you are calculating the work AB plus work BC, but this is 0 because it's constant volume, and just calculate the area under the curve. Again, it's an area of a trapezium. Try to calculate it and check your final answer with this final answer in your PDF file. Now I want to calculate the change in internal energy. To calculate the change in internal energy, I don't have to calculate it on two steps because the change in internal energy could be calculated directly between any 2 points because it is a state function. So I will calculate delta U from A to C directly. NCV TC, the final temperature, minus the initial temperature. This is how you calculate the change in internal energy. Now, the total heat energy is just adding the change in internal energy and the work done. Just add this work, total work, and the total change in internal energy to get the total heat energy. As for the change in entropy, we have two approaches. Either I substitute in the general law. The general law is NCV ln TC over TA plus NR ln VC or VA. Or I can assume that I have a pressure, a constant pressure process from point A, sorry, from point A to point C. If you have a constant pressure process, as if the gas is going straight from A to C, I can use NCP ln TC over T. So you can use this form or the general form. Why? Because the entropy change is a state function, doesn't depend on the path, it just depends on the initial and final. Another example, we have this figure consisting of a constant volume process from A to B, then then a linear relation from B to C. This is a straight line, so it's a linear relation. 0.0175 mole of diatomic gas undergoes the shown process. It's required to find Ta, Tc, and delta T. Required the temperature at A, the temperature at C, and the change in internal energy from A to C. Again, you can substitute in the equation of states at point A and at point C directly to get the temperatures. Now you want to find the change in internal energy. To find the change in internal energy, no need to find it on two steps, just find the change in internal energy directly from A to C because this is a state function, not a path function. When we want to substitute, we can substitute with NCV delta T and substitute with the number of moles, the CV, and the temperature to get the change in internal energy. Or you can use the other form we discussed before. If N is not given, you can use this form. When you multiply NR by TC, you will find PV and another PV, and then you can substitute in this other form. The last example we want to discuss today is 0.1 mole of monoatomic perfect gas going through this shown changes. I want to find the temperature at point A and the temperature at point C, the pressure at B, a work change in internal energy Q, and change in entropy, the total change in entropy. At point A, we have the pressure and the volume, so the state equation will give me directly the temperature. At point B, we have the volume and the temperature, so get the third parameter is the pressure. From B to C, it is same pressure and the volume is increasing with the same percent as the temperature because in constant pressure, the temperature is directly proportional to V. So Tc equals Tb Vc over Vb. You can calculate temperature at C. Now I want to get the work, the change in internal energy, and the Q total. So I will take it one step from A to B, then from B to C, and then add each item. When you are calculating from A to B, how to calculate the work? Calculate this area. Area of a trapezium will give you the work. When you are calculating from B to C, this is the area. So for a total work, you add this and you add this. As for the change in internal energy, you can get the change in internal energy directly, or you can get this and add. As for the Q, just substitute in the first law of thermodynamics. It's the addition of change in internal energy and the work done. How to calculate the delta S? To calculate the delta S from B to C, we can just calculate it using the equation we have. What is required here is delta S B C. Delta S B C. This was some example on the thermal processes. In the next video, we will discuss some example on the thermal cycles and another examples on the entropy. Thank you for listening.